Hi, it's time for another math easy solution. Today we're going to go over a very interesting discovery project, and this is on the geometry of a tetrahedron. Alright, so let's go further, and then note as always, if you don't have time to watch this whole video, you can play this video at a faster speed, and top secret life hack, your brain gets used to faster speed, and you can see my tutorial here, and you could also download and read the notes, as well as reading the notes on the Hive blockchain in article format. I'll put all the links in the description below. And yeah, you can also watch the video in parts, and all the timestamps of all the parts will be in the description, as well as this is a new thing I started doing, is adding video sections playlist. If available, if it's a long video, sometimes I'll break it all down into several parts and then upload those separately, and I'll put a link to the playlist for each one that I do that. Alright, so let's continue further. So calculus book reference. Note that I mainly follow along the following calculus book. This is Calculus Early Transcendentals, 7th edition by James Stewart. And note, in the earlier videos I used the 6th edition. Alright, so now let's continue further and look at sections in calculus book chapter. So I've made a list of the sections in this particular chapter with links to the Hive posts of the videos I've already finished. And note that I've started splitting each long video into sections and made a playlist for each one. And well, here's the ones I've done so far. So here's vectors in the geometry of space. I added a link to the playlist. It has all these videos there. And yeah, these are the ones that I did. And here's the ones I added playlist so far. So the complex numbers as rotation matrices, the dot product and cross product. I split these up into separate videos and added playlist for that in case you don't want to watch the entire long thing. So it's very interesting. And now we're going to go over this one here, Discovery Project, the geometry of a tetrahedron. And that's, the current video. So let's jump right ahead. So topics to cover. Note that the timestamps will be included in the video description for each topic listed below. Yes, and we're going to go over the Discovery Project, the geometry of a tetrahedron, and then go over, well, there's 3 questions to it. I'll go over them all, and then I'll go over each one separately. So let's just jump right in. So Discovery Project, the geometry of a tetrahedron. So a tetrahedron is a solid with 4 vertices, P, Q, R, and S, and 4 triangular faces as shown in this figure, like this. And throughout this video, I'm actually going to be dealing with pretty much a rectangular triangular setup here, or just a perpendicular setup here, where we're at this center point S is all the angles are right angles. I'll be dealing with that. But yeah, this is basically a tetrahedron, is just a triangular pyramid. All right, and then question 1 states, let these vectors v1, v2, v3, and v4 be vectors with the lengths equal to the areas of the faces opposite the vertices, P, Q, R, and S respectively, and directions perpendicular to the respective faces and pointing outward. I'll go over this when I go over each question in detail. And then it says, show that the vectors v1, 2, 3, and 4, when you sum them up, equals to the 0 vector. And remember, when I bold something, it's just, it means it's a vector. And here, I just bolded a subscript as well. Anyways, going further, so question 2, we're going to be going over the volume of, so it basically says the volume of V of a tetrahedron is 1/3 the distance from a vertex to the opposite face times the area of that face. And this one, I don't actually prove that in this video, but I'll do that in a future video. Then part A of it says, find a formula for the volume of a tetrahedron in terms of the coordinates of its vertices P, Q, R, and S. And then part B it states, find the volume of a tetrahedron whose vertices are P, 1, 1, 1, 1, the coordinates, and then Q is 1, 2, 3, and then R is 1, 1, 2, and S is 3, -1, and 2. And then question 3 says, suppose a tetrahedron in the figure has a tri-rectangular vertex. This means that the 3 angles at S are all right angles. Again, that's where getting the this whole setup is all right angles there from the S point. So then it says, let A, B, and C be the areas of the 3 faces that meet at S, and let D be the area of the opposite face PQR. Then it says, using the result of problem 1, or question 1, let's write this, just because I wrote it as question instead of problem, a result of question 1 or otherwise, show that d squared equals a squared plus b squared plus c squared. And this is a note, this is a 3-dimensional version of the Pythagorean Theorem. All right, so let's just jump right in. And yeah, let's look at question 1. And here I added the tetrahedron right here. Yeah, just so it's we don't have to scroll up too high. So question 1, so let V1, V1, V2, V3, and V4 be vectors with lengths equal to the areas of the faces opposite the vertices P, Q, R, and S respectively. So in other words, so if we have this right here, make this a bit smaller. All right, so we have the vector v1. It's going to be opposite of the face, or actually it corresponds to the area of the face opposite the vertices P. So if this is P, the face opposite is going to be right here. So the length of this vector is going to be like that, v1, and directions are perpendicular to respective faces and pointing outwards. So if it's perpendicular to this face, then that means, and it's pointing outwards, well, we're going to be pointing away from it, and let's set everything to the origin. We're going to be pointing downwards away from this face and then perpendicular to that. And perpendicular to that setup. All right, and then V2 is going to be corresponding to the face opposite of Q. So if this is Q, the face opposite is going to be this. So in other words, this is going to be our V2, the length of it, so you put the absolute value sign. And the direction is moving outwards or away from the tetrahedron and perpendicular to this face. In other words, it's going to go over this way. And then V3 is going to be opposite of R. That's opposite of R. So it's going to be over here. That's V3. And then the direction is going to be opposite of it. It's going to be pointing outward. Like that. And then the last one is V4 is opposite of S. That's going to be this entire PQR triangle. That's think of it in 3D, basically the one facing you, and it's going to be pointing outwards away from it, basically directly across. Directly past the page, or like away from the page. In other words, right at your face when you're looking at it. Anyway, so, and then we're asked to show that V1 is equal plus V2 plus V3 plus V4 as vectors, add the vectors up, equals this 0 vector. So let's jump right in. So first of all, because we're dealing with areas of the faces, which are triangles, recall that the length of the cross product is equal to the area of a parallelogram formed by two vectors. So therefore, half that area is the area of a triangle. So in other words, just note that if we had a vector like this, say we had A, and then we had a B vector, let's say there's an angle theta, and basically half of that is going to be, well, the area of this triangle is going to be 1/2, and then the length of the cross product. The length of the cross product, A cross B, as I showed in my earlier video. Where if you ignore that half, you're going to get the parallelogram. It goes like this. But we're dealing with half, so just set up like that. Alright, so thus the lengths of the vectors v1, v2, v3, and v4 can be written as half the cross product of two sides of each triangular face, or triangular face. So in other words, if you have a vector here and a vector here, then half that cross product will get this area. And that's going to be the length of one of the vectors. So let's take a look at this. Let's just draw this out in coordinate form. So what I'm going to do now is I'm going to write this like this. I'm going to draw the triangle. Well, this corresponds to the outward facing face. And let's say this point is P. And let's say it has coordinates. This is on the z-axis. Well, let's just draw the S first. So let's say that there's S right there. This goes out like that. This goes out like this. And this is all right angles, etc. And yeah, that's right angles. Everything's right angles. Even the bottom. And let's just say this is S. And that's the origin. 0, 0, 0. That's the origin. And then this is Q, this is R. Let's say the coordinate of P is going to be the vertical axis, 0, 0, and let's do lowercase p. Like that. And then for R is going to be, well, 0, and then lowercase r, this is the y-axis. And then Q is the, x-axis, so they'll be at lowercase q, 0, and 0, like that. Alright, and now let's take a look. So V1 corresponds to opposite of P, so the face opposite of P. That's going to be, well, this is P. This one's going to be this face, this triangle is going to be our length of the vector V1. Like that. And then opposite of Q is going to be our V2. Opposite of, PQR. And yeah, so that's opposite of V2. opposite of Q, and then opposite of R is going to be over this triangle, and that area is going to be, well, the length V3. And then lastly, the one that's going to be facing up in front of us, that's going to be just this whole PQR triangle. I'll put the V4 vector is equal to, so this V4 vector is equal to, well, the triangle, the area of the triangle P, Q, and R, like that. And now we could write all of these as cross products, and we can do that over here, because again, these are the cross products. So let's look at the V1. So V1 is going to be written as, we could write it as the cross product from SQ and then SR, or the half of that cross product. Let's write the formulas for all of them first, then we'll calculate each one. So V1 is equal to 1/2 the length of the cross product SQ vector cross SR vector, like that. And then V2 is going to be, goes 1/2, and the vector, the cross product is going to be, well, V2. So we go SP and then SR, like that. SP cross SR, like that. And then lastly, we have, or this V3 here, we'll go from SP to SQ, like that. All right, so let's do V3 is going to go for, equals 1/2 cross product SP cross, and then SQ, like that. And then lastly, we'll look at V4. That's this triangular one. So let's write this V4 length equals 2 1/2. And then the cross product will go, well, we'll look at from the top here, PQ, and then we'll go PR. So PQ cross PR. And it doesn't matter which directions you do, because you're doing absolute value. You're looking at the length, so you're going to get a positive number. All right, PQ and PR, like that. All right. All right, now that we have the equations in cross product form for the lengths of all these vectors, let's take a look at, well, calculating these each one, and we could first write that in determinant form. So we can calculate each area by first writing the cross product in determinant form. All right, so let's do the first one. So V1 there. So the length of the V1, let's write it down here. V1, like that, is equal to 1/2. And then this is a SQ, and then time across SR. So SQ and SR. SQ cross SR, like that. And now this equals to, in determinant form, I'm going to put, well, first we need this absolute value sign because we're dealing with the length of the cross product, because the cross product gives a vector. And then we put another line for the cross product, another line is for the length. And then we do the components I, so recall from my earlier video, J, and then K, so recall from my cross product video. All right, so that's what we have, and then there's another length like that. And then we put the components, or the, so each of the vectors. So SQ, well, it's going from S to Q, and then so recall that to get the position vector, we just Q minus this point here. So Q minus S for each component, but this is the origin, so then basically that is the position vector. So this is going to be Q, 0, 0. Then the R is going to be 0, R, 0. So this one is SQ is the x-axis, has a value Q, then 0, 0. And then SR, that just has the point at the y-axis, R, 0. All right, so this equals 2. Let's put the 1/2. And then the next one as well, we're doing it length, so let's put that line there. And now remember the setup, so we would cross this out, and then we'll go 0 times 0 minus 0 times R. So in other words, we'll have a 0 minus 0, like that. And that's for the I component. Now we could erase this. Now the next one is going to be, well, minus, and then we cross this, cross the center. Now we go Q times 0, and then 0 times 0, that's again going to be a 0 vector. J, like that. And then the next one is going to be, well, let's erase this. We'll cross this, cross that. And this is going to be plus, and then this is, this is from here, across this one. That's going to be QR and then 0 times 0. So we'll get a Q times R minus 0, and this is the K vector, like that. Yes, we block it off like that, erase this, and now we have this. And all these vanish, so we're just going to have a 1/2, and then the length of the component QR K vector, the standard basis vector. This equals to, well, just write this in the other format that we're used to, just so we don't get rid of these. This is just going to be the same thing as writing the 1/2 length from 0 component, 0 in the X, 0 in the Y, and then QR in the Z component, like that. And then recall the length is just going to be square root, so we'll do 1/2, then square root, and then all the components squared. So 0 squared plus 0 squared plus QR squared. Then all these vanish, and then this square root cancels the squared. We're just left with 1/2 QR. So that is the length of the component. And note that it only has value in this Z component. So that's the only part it has, and the length of that is going to be, well, 1/2 QR, and you can just multiply that inside. And now if we look at the direction, and that's where I've written here. So since we are told that the direction of the vectors point outwards, perpendicular from the faces, then the vector v1 must be pointing downwards away from the tetrahedron. Yeah, so we have our cross product is this. So and the length of it is going to be this one here, and we're told again that the length of that cross product, or the half that length, is going to be the length of that vector. So that gives us a clue as a direction. It's going to be on the Z component, and notice the face right here. So that's this one right here, and it's going to be pointing downwards, perpendicular away from the tetrahedron or away from the face, be downwards like that. So if it's pointing downwards, and then the length is going to be this, then we could just, well, plug that in for the Z component. So what we have is v1 vector is equal to, well, basically this one here, but it's pointing downwards, so negative. 0, 0, then negative 1/2, multiply that 1/2 inside QR, like that. And there is our direction. Yeah, so there's the vector with direction there. Alright, so going further, so similarly for the remaining 3 vectors we have, so let's write v2 now, and again write it a bit more down, because we're going to write the determinant form of the cross product. So v2, the length of it is equal to, well, 1/2 in the cross product, and it's what right here, SP cross SR. So SP as the vertical, and then SR here to get this v2 there. And then, so SP and SR, those are the coordinates. This is the Z1 is the Y1. Alright, so SP and SR. SP cross SR, like this. This equals to 1/2, and then the cross product. So we'll put a length like that, and then the determinant form. So I, J, K, like this. And then put the determinant, and then the length. And then IJK, so the P1 right there, that's going to be, well, the Z component 0, 0, P. And then the R is the Y1, so 0, R, 0. Alright, so let's just solve this cross product. Alright, so let's just write this down. So 1/2, and then put the length or the absolute value sign. Then do the same setup as before. Cross this, cross that, and then this times this, minus this times this. That's going to be, well, 0 minus PQ or PR, like that. And then this is going to be I component. And then the next one's going to be minus, erase this. Well, we could keep the top one actually always on there. And this next one's going to be across the middle. And that's going to be 0 times 0, 0 minus P times 0, 0. And then J, like that. And then next one's going to be, well, erase this. It's going to be this one right here. So that's going to be, well, again, another 0 times R, 0 minus 0 times 0, 0, okay, like that. And then put the length sign like that. All right, so that's what we have. And everything vanishes except the first term. So we're left with 1/2, and then 1/2, and put the length like this. Negative PR. and then I component. And then in the other setup that I like is, just put the 1/2 there, just keep it out of there. Easier to write. It's going to be, we'll also forget to put the absolute value sign or the length. So negative, and then this is going to be negative PR, and all the other terms are 0 and 0 for the Y and Z components. And like that. Alright, so that's what we have. And now plug this into the length formula, the square root, and we'll put the 1/2 outside. And then each term squared, so negative PR squared plus 0 squared plus 0 squared. And yeah, again, we're dealing with the absolute value sign, so you could go with negative right here squared would be positive, and then we're just left with PR, so this will cancel, etc. And we're dealing with absolute value sign, so it's going to be 1/2 PR, like that. And all the other terms get out. So it's the absolute value is that, or in other words, the length. And now the vector v2 is going to be equal to, well, it's going to be, let's take a look. So notice that the cross product only has it in the x component. And if you look at the face right here, so there's the face, there's the area, and it's going to be perpendicular and pointing outwards. In other words, it's going to be pointing outwards this way. Perpendicular to it, will start from the s value, and it's going directly opposite of q. I mean, or the directly opposite of q, this face, and this x-axis there. So basically, it's going to be just this thing. So in fact, this cross product is actually the same direction that we are going to have. Then put the negative 1/2 inside. It's going to be negative 1/2 PR, and all other terms are 0, like that. And then when you take the length of this, you're going to get this right here. All right, so circle this. And now the next one is v3. All right, so the length of v3 is going to equal to 1/2 the cross product of, well, SP and then SQ. So that's v3 is over here, so SP and then SQ. Let's write this down. So SP and then cross SQ. Like this. And now this equals to 1/2 and then length determinant I, J, K. Alright, so we have that. And the components P is going to be, well, 0, 0, P. And then the components the coordinates of this Q there is going to be, Q is just Q right here, 0, 0, because P is the z-axis, Q is the x-axis there. And now, alright, and now what we'll do is the same thing as always. So this equals to 1/2 length, and then let's take cross this out, and then block this out. So 0 times 0, and then P times 0. It's going to be, well, 0 times 0, 0. Minus 0 times P is 0, and then this is going to be I, like that. Block out I, and then minus, and then this is going to be erase this one here. So 0 times 0, and then minus P times Q. 0 minus PQ, like that. And then this is going to be I. And the next one's going to be, let's block this out, like this. And then the next one's going to be plus, erase this line, cross this out. So 0 times 0, those are all just zeros. 0 times Q is 0. And that's the K component, like that. Alright, so we have this, and we have that. And then everything else vanishes, so we're going to get 1/2, and then put the length like this. This vanishes, and this one becomes negative, and the negative becomes PQ, and then J, like that. And then the other one is 0, so the length of that, just write this in the component format here. This is going to be, well, 0, well, again, we're dealing with length. So we're doing the length of that, and then this is PQ, and then 0. Like that, and then take the absolute, or take the Pythagorean Theorem, the triangular one, to get the length, like this. This is going to be, well, 0 squared plus PQ squared plus 0 squared. So the absolute value of the length is going to be, yeah, then this all cancels. We're just left with 1/2 PQ. So that's the length. And to get the direction, we know it's opposite of the face. So, and V3 vector is equal to, this is going to be equal to component like that. And notice again, from this cross product, it only has the y component, and that is actually what we also just need. So we have it here. It's opposite of this face and pointing outwards. So it's going to be pointing this way, perpendicular to it. And that's going to be directly parallel with this y-axis. So that's going to be minus PQ. Let's just erase this and erase that. Let's make it neater. Yeah, so directly opposite of that. So that's the length. We're just going to go this right here. Put a minus sign and also put the 1/2 inside. 0, negative 1/2 PQ, and then 0. Like that. Box this whole thing in. All right, and now note that for the length of V4, put a bold here. This one, since it involves vectors not relative to the origin, we need to calculate the position vector, which is again the equivalent vector but starting from the origin and is the difference in each coordinate component. So it's going back here. So this is going to be V4's 1/2 PQ PR. So PQ PR is like this, and then PR is like this. So notice that none of these are starting from the origin, whereas all the other ones we had were starting from that origin. Okay, it's jumping up over here. Put a dot. So all the other ones were starting from the origin, from the origin. So to get that equivalent one to the origin, we just take the difference. So we'll go Q minus P, and then that will be the equivalent. So if this is the vector like this, it's going to be the equivalent vector here, and so on. And then this vector here, QR, for example, or PR, is going to be shifted here. So this vector here, we can shift it here by taking the difference. All right, just erase this. All right, erase that. And let's scroll down here. All right, so let's write this down. So V4, the length, is equal to 1/2. The cross product, again, the cross product for this one is PQ-PR. So PQ and then PR. So we'll do the position vector. So Q minus 0, 0 minus 0, and then 0 minus P there. And then, yeah, PR, and then R minus that there. So let's do PQ and then PR. And yeah, see if we have that correctly. Yeah, PQ, PR. All right, so PQ cross PR. This equals to 1/2 the length. Then there's a determinant. Put the I. Let's make more room because we'll be doing some subtraction. J, then K, like this. Length. Determinant and then length. Do that again. Determinant, length. All right. So PQ. So Q minus P. Q only has terms in the X component, and P only has terms in the Z component. So put a minus P here. So minus 0, 0 minus 0, and then 0 minus P. And then the R only has components in the Y one, and that's going to be R's here. And we're doing R minus P. Then P only has it in the Z, like that. And we're subtracting the other way around. So we're going to have 0 minus that, R minus 0, 0 minus 0. And simplify this out. This equals to 1/2. And 1/2 determinant, length, determinant. I, J, K, like that. Length, determinant length. This is going to be Q, 0, and then negative P. So just subtract all these, get rid of the two variables, put 1 or 2 numbers. 0, R, negative P, like that. Now this equals 2, let's put it down here to make it neater. Length, and then this is going to be, cross this out. We're going to go 0 times negative P is 0, and then minus 0, minus, and then this is going to be a negative P times R, so negatives cancel, becomes positive PR, like that. And this is the I component. And now we'll do subtracted by, get rid of this, cross this out. So Q times negative P is going to be negative PQ minus and negative p times 0, 0. This is the j component. Now the next one is going to be plus, get rid of this, cross this. So we're going to have qr minus 0 times 0, 0, and then this is k. Like that. That's fascinating stuff. And then put the length, right, this dot here. All right, so we have that. So this equals 2, simplify everything, cross like that. So length, PRI, then minus cancels, becomes PQJ, like that. And then plus QRK, like that. And then just for completeness, because the other one we wrote it all in the component format as opposed to the standard basis one, but even though this one's pretty straightforward, it's going to be PR, PQ, and then QR. Just because we did it for all the other ones, and it's be length, length. So this equals 2, 1/2, and then the square root of everything, PR squared, and then this is going to be plus PQ squared plus QR squared, like that. And yeah, we could just keep it like that. That's pretty straightforward. So that's the length. And now the component of it, and the vector itself is going to be equal to, well, so we have this number, the cross product is there with the 1/2. And notice in all the other ones we did, the cross product basically is the exact same vector, but we had to choose a direction based on what we were told. So this one here, if we look at this face PQR, like that, so basically we're going to have to go outwards from it. So in other words, this is going to be pointing outwards in a positive direction as opposed to the negative. It's either positive or negative, and in our case it's going to be positive. So notice all these other ones we just took accordingly. We took this one's going to be negative. This one we took positive. This one's also negative. Then the V3 was was negative as well. This one is positive. So the only one that's actually positive is this one. So all these are going to be positive. So we'll just put these all down and multiply the 1/2 inside this cross product setup there. This is going to be all positive. So 1/2 PR, 1/2 PQ, 1/2 QR, like that. All right, box this in. All right, so now that we have all these vectors, note that the vector V4 is pointing out of the page in the positive direction away from the PQR triangle. And yeah, so now therefore, if we add all the vectors, we get, so let's just write these down. So V1 vector plus V2 vector plus V3 vector plus V4 vector, like this, equals 2, and this is going to be blank. Not blank, that's going to be the component there. So let's write the V1, it was above here. So V1 is 0, 0, and then negative 1/2 QR. All right, so this was 0, 0, then negative 1/2 QR, like that. And then put a bracket like that. And we're going to be adding, so this is going to be plus. The next one is going to be V2. Is negative 1/2 PR and then 0, 0. This is going to be negative 1/2 PR 0, 0, like this. And just put it like that there. And here I just made this big space there because I want to try to make it line up somewhat. And now the next one is going to be, well, plus V3. And V3 is right here, 0, 1, then minus 1/2 PQ. And then 0 there. So 0 minus 1/2 PQ and then 0, like that. The next one is going to be, well, this right here, 1/2 PR. And then 1/2 PQ right here, then 1/2 QR. So notice what happens here. All these cancel out. So this cancels with this. This cancels with this, and then this cancels with this. Yeah, so these all just cancel. In other words, we're just going to get left with a 0, 0, 0. In other words, the 0 vector epic stuff. And yeah, if we scroll back up, that's exactly what we were asked to solve, and that's right over here. So question 1, So we were given these vectors with these conditions, and we showed that the summation of all the vectors equals to the 0 vector. All right, and now let's go over to question 2. And just a note on question 2, I actually finished filming the video, and then I realized that the actual calculus book had a mistake in it, and then I thought I might as well redo this and add more clarity, even though the final answer is still the same. So question 2, the volume V of a tetrahedron is 1/3 the distance from a vertex to the opposite face. And here's the correction, MES correction. This is actually the height of the tetrahedron. So it's not actually the distance from a vertex to the opposite face, but it's the height of that tetrahedron from this opposite face. And I'll illustrate that in a bit. So times the area of that face. And again, I will look to provide a proof in a later video. And now look at question A. So question A states find, or part A of question 2 states find a formula for the volume of a tetrahedron in terms of the coordinates of its vertices P, Q, R, and S. And then part B states find the volume of a tetrahedron whose vertices are P, 1, 1, 1, and then has Q is 1, 2, 3, and then R is 1, 1, 2, and then S is 3, -1, and 2. So let's take a look at solution to part A. So after finishing the filming of this video, I realized that the formula for a tetrahedron as stated in question 2 is actually wrong. So that's not actually the formula. The actual formula, and here I added a link to the Wikipedia article, involves the height of the tetrahedron and not the distance from vertex to opposite face. And this is evident from a skewed tetrahedron. And here I'll draw it out. So let's say we had a tetrahedron like this, something that's not symmetric like this. And yeah, so let's say there, and then inside there's the point like this. So there's the inside triangle, and there's the 3 triangles around like that. And let's say there's an area here in this base there. And so the opposite vertices is somewhere here. So the distance from this face to that is going to be, well, something like that. But that's not actually what we want. The actual formula involves the height, h, like that. And the volume of this tetrahedron is equal to V, 1/3 the height times by that area. So this is the volume. Yeah, so it's equal to, yeah, so 1/3 the distance is actually, it's actually the height. So 1/3 the height times the area of that face. So from this area up to there. So that's the actual formula. All right, and going further, I think what the Discovery Project actually meant was the distance to the plane that contains the opposite triangle face, which is the same thing as stating the height of the tetrahedron. So this distance right here is the same as saying that the distance from this point to the opposite face, or to the plane that consists of this opposite face. If we had a plane like that, just have it in 3D like that, and this triangle is inside this plane. So the distance from that plane that contains a triangle to that point. I think that is what they were considering. Let's erase all of this. All right, so yes, going further. So thus we can write the volume of a tetrahedron in coordinate form as follows. And first what I'm going to do is I'm going to actually draw that skewed tetrahedron again, just so it's more clear. So that, yeah, we're not dealing with, yeah, so we're dealing with a height. So let's just draw this out. I'm going to draw it like this. And there is our triangle. And then inside has a point, say this point like this. And I'm going to call the point inside here, I'm going to call it P actually, instead of the S. I'm going to say this point S. And it has coordinates S1, S2, S3. And then let's say, and then the height here, or the distance to the plane that contains this face right there. This is going to be our H, like that. And then this point right here is, let's say this is our R. It says R1, R2, R3, and then this point right here is going to be, let's call this Q, and this coordinates are Q1 lowercase, Q1, yeah, Q1, Q2, etc. And Q3, and then at this point right here, we will call this point P. And I'll put this like this, so that is our P. And the coordinates are P1, P2, and P3. Like that. Alright, so now that we have this set up, so we could write the volume as, so we could write V equals 1/3 H times by the area of this opposite face, which is P, the area of this PQR triangle. And now what this equals to, well, let's write down our terms. And then the height is, let's call this, let's write this in terms of the distance to the plane, just so it's generic. So distance, we'll call it D, from the plane. So we're going to go from this point right here. So we'll go from S1, S2, S3, and then that distance all the way up to the plane that contains PQR. Like that. And then the area of this triangle, we know that already. That's just this vector right here, this PQ and this PR. And let's put this P as well there. And the coordinates are P1, P2, P3, etc. And so we have this. I'm going to shift this over like this. And then now this one here is going to be multiplied by the area of this. And then we already solved that earlier, is 1/2 the length of the cross product, PQ cross PR. Like that. Alright, and now I'm going to box this in, and the solutions that I found online, I can find the solution manual. The solution I found online just stopped at this point, but I'm going to keep going further and get the exact stuff they're asking for, which is in coordinate form, because this one just says, well, the distance and so on, but we don't have a formula yet for the distance. Alright, and now that we have this, let's just keep going further, and we're going to look at now the equation of a plane, because here we have distance from this point S, from the point S to the plane PQR, or that contains this triangle PQR. So let's write the equation of a plane. So note that the equation of a plane can be derived based on the fact that the dot product is equal to 0 for perpendicular vectors. And yeah, I haven't covered equation of a plane before, so it's a good time to start now. What I'm going to do is let's just draw a plane like this. And when we talk about plane, just basically a rectangular in 3D rectangle, etc. And now what we're going to do is, I'm going to put the x and y axis, put it like this. So that's y, and there is our x. And this is our z, there's the origin, 0. And let's say we had a point here. I'm going to call this point over here is at x0, y0, z0. And let's say there is a just vector like this. And this goes to the x, y, z, and a point right here. So it's a vector like that, and this could be anywhere. So that's the whole idea of a plane. So anywhere around this perfect rectangular sheet right there. And now, and then this can extend to infinity, etc. if it's not bounded. So now what we'll do is we're going to use the fact that the dot product is equal to 0 for perpendicular vectors. So if we take a vector perpendicular to this plane, like this, so this is, let's say this is perpendicular, and we'll call this n, or normal to it, or perpendicular to it. And let's say this has the components for this vector, capital A, capital B, and C, like that. Yeah, so thus the dot product of this of these two perpendicular vectors, where we can get the position vector over from here to here by subtracting. So what we'll get is, well, we'll go A, capital B, capital C, dot, and then the position vector of this vector right here. Position vector, all we do is shift it over to here, etc. And likewise for this one there. Yes, and this vector right here, this is actually the position vector. So this is the same thing as over here and so on. So, but these ones are the coordinates, so then we could get the position vector, and let's just write that down, and that's going to be, well, just the difference. X minus x0, and then y minus y0, and then z minus z0, and then recall from my dot product video, if they're perpendicular, that's equal to 0. So, and now we could just do the dot product. Remember that, we just multiply this by this, b by the middle, c by this one, add them all up. So we just multiply by the components and add. So what we get is a x minus x0 plus b y minus y0 plus c z minus z0, and this equals to all 0. And you can stop right here or continue further. I'm going to continue further and simplify it. So that's one way of writing the equation of a plane. The next one is you can expand this out. This equals to, well, a times x, then minus a times x0, but we'll do that after. So a times x, and the next one is b times y plus c times z. B times y plus c times z, and then minus when you do this all together and then add those up, we get this ax0 plus then this b times y0, and then c times z0. Like that, this equals to 0. Alright, so now that we have this set up, and what I'm going to do is, well, I'm going to call this lowercase d, and then just write this out as ax plus by plus c z minus lowercase d equals to 0. So this is the equation of a plane that's usually given. Alright, so now that we have the equation of a plane here, now the next step is, well, we need to find the distance from a point to a plane, because remember this is the distance from the point S to the plane PQR that contains the triangle PQR. So, and the equation for the distance from a point to a plane which I'll prove in a later video, is given by, just a bit out of the scope for this video right now. And let's just put this down here. Let's just do some drawings again, just to make it clear. Let's say we had a plane like this. This angle like that. So this is a plane, and this has the equation ax plus by plus cz minus d equals to 0. So let's say we had like that, and let's say we had, this is our y, this is our x, and this is our z, like that. 0 point. Let's say we had a point P. Let's say the point P is here. And this point is has x, or instead of just putting a point P, because we already have P for something else, let's say this is x1, y1, and z1, like that. All right, so now the distance from here all the way to this part right there, it's going to be perpendicular to it. So let's just draw this a bit better. So let's write this plane here. And let's say this point like this goes across, let's say it goes all the way across here, and it's going to be at a right angle to it, because it's that's the closest distance to it. And this point right here, we'll call this D. So from there, or from this distance, like that, let's call this D. Like that. So that is the distance d, and d is given by the formula, which I'll prove in a future video, ax1 plus by1 plus cz1 minus lowercase d, divide this by square root a squared plus b squared plus c squared, like that. That is the distance d. And let's bold all, or box all this in. Alright, so thus putting this all together, the volume of a tetrahedron in coordinate form is, we're going to have v equals to, well, 1/3 the distance to the plane, or the height, and we'll put a giant bracket like this, a, and instead of this x1, y1, z1, we're going from the point s1, s2, s3, etc., to the plane PQR, and there's the area of that triangle. So that's going to be S1 plus B S2 plus C S3, and then minus D, like that. Divide this by, this is going to be A squared plus B squared plus C squared, and then bracket, and then this is the area of the triangle. It's going to be 1/2 the length of the cross product PQ cross PR, like that. And yeah, that's what we have. Let's just go look at the formula we had. So there's distance, and there's the 1/2 PQ times or cross PR, which is quite fascinating stuff indeed. I'll move this into center. And yeah, this is some epic stuff right here. And I'm going to do is I'm going to box this whole thing in, or actually box the entire volume in, like this. All right. And then I'm going to write here, because we need this A, B, C, etc., where the ABC, well, that is, again, that's going to be from a vector perpendicular to this plane. Because remember this equation right here, perpendicular to the plane, In other words, if we go back up here, it's, well, we have a perpendicular plane right there. That's our n. There's our PQ, yeah, PR. So in other words, it's a cross product. So this is going to be where PQ cross PR is going to be, oh, this is a vector, equals to, well, just the vector A, B, C. And we're also given, so we're that, and we know that this D is equal to, well, if we go back upward, what D is A x0 plus B y0 plus C z0. And again, if we go back up here, so we have this part, this is our n. So this is going to be our P there. This is going to be our x0s, y0s, etc. So that's our n. In other words, that's going to be this point right here. That's just the point P. And that's where we take the cross product from. So then we replace the x0 with the P coordinates. So that's going to be where D is equal to, well, A, this is going to be x1, P1. P1 plus, for our case, yeah, B, P2 plus C, P3, like that. So that is our D. And we can illustrate this by, and actually before that I'm going to do I'm going to box this in. So this is part of this equation. So this throws it all inside. And then note, just to illustrate that, draw our skewed triangle, or tetrahedron, is like this. This is point S. Point P is inside. Goes dashed line across. And then this is going to be a dashed line across. And this is our R. This is our Q. And then our cross product goes up like this and goes straight across it like that. This is our N, like that. And there's our point P. And this N is again equals to, let's put this N like this. Let's move this down. Yeah, move this down. And yeah, write this back again. So N, and that is our perpendicular vector, and that's just going to be the PQ. So PQ from this angle, from this this vector to this vector, cross those, and we get cross PR, like that. So yeah, that's what it is. Alright, so now that we have this, and yeah, this is more detailed than the solutions that I was able to find online, but they weren't the official ones. But anyways, it's pretty in-depth. You could even throw this in a computer program and solve it all. Alright, so that's what we have. So let's go back to, well, question, the part B of it now. So question 2, part B, says, find the volume of a tetrahedron whose vertices are P111 and Q123 and R112 and S3 minus 1, 2. So let's write these down and start solving it. So solution to part B. So the first step is to derive the position vectors PQ and PR and then compute their cross product and cross product length. So, well, let's write the point P is 1, 1, 1, and then the next point is Q is, well, 1, 2, 3, and then R is 1, 1, 2. And we'll deal with the S later. So let's just double check that. And double check it is 1, 1, 1, 1, 2, 3, 1, 1, 2. All right. So that's what we have. And the position vector PQ is just a difference Q minus P. So we're going to have write this in vector form, the square bracket or the triangle bracket. So 1 minus 1, 2 minus 1, and then 3 minus 1. Like that. And now this equals to, well, 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. That's position vector for PQ. The next one is PR. Alright, PR is equal to, well, 1 minus 1. And then we'll have this 1 minus 1. And then 2 minus 1. And now this equals to, well, 1 minus 1 is 0. 1 minus 1 is 0. And then 2 minus 1 is 1. All right. Alright, now that we have this right here, let's solve the cross product and then do the cross product length afterwards. Because again, we'll need the cross product for this ABC, and then the cross product length that we need that for this area there. So let's write this down. So PQ cross PR is equal to, and then write this in indeterminate form. And let's move this down a bit because we're going to write this in the giant determinant. I, J, K, like that. The next one's going to be 0, 1, 2, then 0, 0, or 0, 0, 1, like that. Alright, this equals 2, well, let's just solve this out. So again, as always, you cross this, and then you multiply this by this, and then subtract by this by 2 times 0. So we're going to have a 1 times 1 minus 2 times 0, 0. This is going to be the I component. Alright, erase this. Now the next one is here, so we'll do a minus. The middle one's always minus. 0 times 1 is 0, minus 2 times 0 is 0. J, and the next one's plus. Erase this. Cross this. The next one's going to be 0 times 0, minus 1 times 0 is also 0. This would be K, like that. Alright, that's what we have. Alright, so that's what we have, and now we could simplify this further, get rid of all the zeros. This is going to be, well, I. So 1 times 1 is, we have 1 times I is just I, or 1I. And all others vanish, and that's all we're getting is just the I component. In other words, in writing this in the other component set up like this just equals to 1, 0, 0, like that. And where again, this cross product is going to be, we're going to need it for our equation. That's just our A, B, C. In other words, all the B and C are 0, and then A is 1. So that's what we have. And now the area PQR, remember this is just going to be 1/2 the cross product length. 1/2 cross product length like that, PR. And this is going to be equals to, well, 1/2 of the length of this this vector I, which is, well, again, this is just going to be 1/2 square root, and then 1 squared, all the components squared, 0 squared. Well, 0 squared, these all vanish, it just becomes 1 squared, this is 1, this is equals to 1/2. So the area is 1/2, like that. Alright, so now that we have this, the next setup is to find a distance from the point S, which has coordinates 3, -1, 2 to the plane, to the plane PQR. So let's write this down. So we have our points, this S right here, this is a 3, -1, 2. In other words, this is the coordinates S1, S2, S3 that we were looking at. And that is for the equation. So there's S1, S2, S3. And we already know what ABC is. ABC is this right here. Yeah, so let's just write that down. So we know that the normal vector of the plane is equal to, in our case, PQ cross PR. And this equals to 1, 0, 0. And then we have it, this equals to, well, A, B, C, like that. Yeah, in other words, we have A equals to 1, and B equals to C, which equals to 0. So just circle these like that. That's what we have. And then we also have this right here. And then the next setup is, well, we need to solve our D. And this is the point P. And the number of the coordinates of P is just 1, 1, 1. So let's write this down here. So we also have, let's just write that down. So P, this is P1, P2, P3. This equals 2, P1, 1, 1. All right, so we have that. So all those are equal to, 1, 1, 1. So so then this means that the lowercase d is equal to A P1 plus B P2 plus C P3, and A is again just 1, so 1 times 1 plus, and then B times, well, B0. This is equals to 1, like that. All right, so that's d is equal to 1. So in other words, we'll have this right here. The distance d is equal to, that distance is just this whole part right here. And we already know that d is, etc. So let's just write that all down. A S1 plus B S2 plus C S3 minus D divided by square root A squared plus B squared plus C squared. This equals 2, and then A is just 1 times S1 is 3. Minus, plus, and then B is 0, plus C is 0, minus D. D is just 1. Like that. And then divide this by square root. A squared is 1. Yeah, I mean, A squared is just 1 squared. Plus all the others are 0 squared. 0 squared. So in other words, all we get is, well, this becomes 3 minus 1 over 1. Because this is just 1 squared and then square root. This equals to 2. So the length is 2. All right, and so the distance from the point to the plane is 2, but we can do a double check right here. Let's do a double check. That was using the equation, but first we got to find the equation of a plane. So we have the plane is just going to be, well, if you just remember it, ax plus by plus cz minus d equals to 0, and d is just 1. Then a is just, we already know a is just 1, everything else 0. This becomes 1 times x minus 1 equals 0. So in other words, we have x minus 1 equals to 0, or x equals 2. Shift the 1 over to the other side, x equals to 1. So this is the equation of a plane in 3 dimensions. All right, so let's graph that out. So let's say we had the plane like this. I'm going to draw this plane like this. All right, so that's the plane, and let's say we had this point goes out like this. This is the x-axis. It goes through and over here, and this is the y. This is the z, I mean. And at this point right here is 1. So that's x equals to 1. So this is the x equals to 1 plane. And this is our y, like that. And let's say our point was the 3, or our point S is going to be, well, 3. Let's say this is 2. Let's say this is 3 now. So this is 2 here. And then it goes -1. So here, like that, -1. And then it goes up to 2. Somewhere around here. And this is our point S. I'll put point S. Point S, which has coordinates 3, -1, 2, like this. And basically what this is saying is, well, the distance from here to here, perpendicular to it, is just going to be directly across on this x-axis, because this is perfectly straight with this x-axis. That's going to be this 3 minus 2. 3 minus 1 equals to 2. So we have double-checked that. That's exactly it. All right, now that we double-checked that, let's write this a bit better, like this. And now the next step is, well, let's just put it all together. So thus the volume of the tetrahedron is, and write this out, so V equals to 1/3 times d, the distance from, well, the point S to the plane. Let's put these all down, PQR, and then times it by the area of the PQR. Area PQR, this equals to, well, 1/3 times the distance can be 2. Times it by the area, number is 1/2, and yeah, just to double check. So there's the this is the distance 2, area is 1/2, and these 2 cancels, and this equals to 1/3. Epic stuff. All right, and now let's go even further, and let's as a double check, we can graph the tetrahedron and calculate its area using the GeoGebra, or just using GeoGebra, which is an amazing 3D graphing calculator and other kind of calculator here. So here's what I've graphed. So here's the points P, Q, R, and S, and then I made a pyramid, PQRS. In other words, just a triangular pyramid is a tetrahedron, and then we get something that looks like this, and it actually calculates area too. Area is equal to 0.33. In other words, 1/3. So we got that right. And then when you shift this around, and you see this perfectly in line with the x equals to 1 plane as the x-axis, this is z, there's the y, etc. And also note that, again, if you have this plane here, notice the distance to the point S, or the perpendicular distance, or the height from the plane is exactly 3 minus 2. So there's 3, there's 1. So this distance is just 2. Yeah, so that's just 2. So yes, epic stuff here. And now if we go to this link, so here's a link, you can play around with it, and so on, and it looks like this, and you can move it around, and so on, which is quite amazing. And you can adjust it as well. You can move this. I think you could also drag and drop. So you can change it around, and you see the area automatically changing, and so on. And let's do a Control Z back there. Yes, epic stuff. And again, notice perfectly in line with the with this right here, with this x equals 1 line, and there's a distance 3 minus 1 is 2. So that's the height. Yes, epic stuff. All right, let's continue further and look at question 3. And this one states, suppose the tetrahedron in the figure has a tri-rectangular vertex, and that's what I was assuming the whole time, vertex S. This means that the 3 angles at S are all right angles. And it says, let A, B, and C be the areas of the 3 faces that meet at S, and let D be the area of the opposite face P, Q, R. And then using the result of problem 1 or otherwise, show that D squared equals A squared plus B squared plus C squared. And this is a 3-dimensional version of the Pythagorean Theorem. And yeah, let's just take a look at the solution quickly. So using the results from question 1, the areas of the faces are as follows. So basically, we just draw a tri-rectangular vertex right here, or tetrahedron, the tri-rectangular, or a tri-rectangular tetrahedron. So let's just write this down. So basically what it's saying is, if you have this triangle, we're going to draw the original triangle, the original tetrahedron. There's P, there's Q, there's R. And this goes like this all the way to S. And this goes like that. And these are all right angles. This is at S. Like that. And this is at so tri-rectangle. So this is a tri-rectangle, rectangle, or the 90 degrees. So that's S there. And now the areas A, B, C are the areas of 3 faces that meet at S. So 3 faces are right here. So we'll call this one A, call this B, just to make it line up with V1, V2, V3 that we had earlier. And this is C. And then D is the opposite face PQR. So D equals to the area of the PQR, like that. All right, so now using the results of question 1, we can get the area. So basically A, this one A is just equal to, well, the length of the V1 vector. This equals 2. Let's just scroll all the way back up and see what we had. And this is all the way up above here. So that's the V1. Yeah, this one is just 1/2 QR. So remember, V is the opposite of the P. So the top here, P. So this would be V1, this is V2, V3. So in other words, A, B, C, and D. And the answers we had were right here, 1/2 QR is V1, then 1/2 PR. And then the other one's PQ right here. Then lastly is this one here. This is a V4, and this has all of them: PR, PQ, QR, etc. And you could just move this 1/2 inside, and so on. So let's put this all here. So this equals 2. Yeah, so 1/2. This is QR, and then B. This was just equal to V2. This equals to 1/2 PR. And then C is equal to the V3, 1/2 Q, not this PQ, I mean. Like that. And then D is equal to the V4. See if I remember this one correctly. This was just 1/2 square root, and then this we had a PR squared plus a PQ squared plus a QR squared. So the order is a bit different. All right. All right, and now this one, we can just put this back inside. So you could do let's put it for completeness. This is going to be square root, and then this is going to be 1 over this is squared. So squared, square root, just get it out of there. And this is like this. This is, and then shift this around. So move this QR in front, like that. QR squared, so it matches up with this A. And then PR is in the middle. This is going to be PR squared. Plus the next one is PQ is a C. So move this one over to this side, like that, and so on. All right, and just box this in. This equals 2. And yeah, put this 1/2 inside every single one. So again, we get, this is a lot of this is just redundant, but it's pretty straightforward. So 1/2 QR, and then all squared, and then 1/2 PR all squared, plus 1/2 PQ all squared, like that. All right, in other words, this is just our A. This one is going to be our B is our C, and so on. And all squared. So, and then we could also, yeah, this is going to be our D. This is, so basically this is D. But now if we square both sides, square, square, etc., and then we're just going to get the 3D Pythagorean Theorem. So this is going to be, yeah, this is going to be our A. So this is our A. This one's B. Yeah, B squared plus C squared, like that. And there is our answer. That's what we're asked to solve. And yeah, this is 1/2 QR, PR, PQ, and then etc. Shift this around and make it all the exact same. So 1/2 QR, 1/2 PR, 1/2 PQ. Line up, so ABC. Yeah, so that's exactly this. So using the result, we just show that it's equal to, well, D squared equals A squared plus B squared plus C squared. So epic stuff. And yeah, three-dimensional Pythagorean theorem, very amazing. Anyways, that is all for today. Hopefully you enjoyed, and yeah, let's just scroll back up. And like always, yeah, you can download these exact notes in a link in the description below, and I'll putting the notes in PDF format as well as an article format on the Hive blockchain, as well as adding playlists to sections of all these. So I'll split up all the questions and other stuff into it as separate videos, shorter videos. But if you want to watch a long one, it's going to be here, and I'll be referencing this long video in all of them. And also just shout out for my Telegram to check it out. MES links right here. So t.me/MES links. This is where I post my real-time research on all things math, science, conspiracy, and so on. Pretty epic stuff. So yeah, make sure to follow it. Daily, it's pretty epic stuff. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy Solution.